Good evening, everybody. This evening, as you well know, Ed Bothamley has been a member of our society for about 5 years now, I think it is. It's soon added up. He has reignited an interest in astronomy that began one teenage night in the 80s when he was wondering why the plough had moved. He went on to study astrophysics at Manchester University, but transferred to mechanical engineering when he realised he didn't understand Einstein. And perhaps still doesn't, I don't know. After graduating, he worked for a local sweet manufacturer and then as a science teacher, but now works as a sales engineer. So could everybody please put their hands up and welcome tonight's speaker, Ed Bothamley.
Thank you. Okay, so hopefully you can see my front page.
Yes.
Okay, well, so hopefully I've put photo credits throughout, but if there are none, that's because they belong to reaction engines or I've created the screen and it should be obvious which is which, to be honest. Why is that not changing? I'll have to use that then. So the main source for this talk has been the website of Reaction Engines. That's reactionengines.co.uk. And on YouTube, there's a talk on Skylon by Jamie Wakefield, who's a Reaction Engines employee. And you can perhaps, let me put pointer on. And just up here, you can perhaps see Skylon update. That shows us the latest stuff as of 5 months ago. I've used that also. So this evening I want to try and answer the question, why do we go on holiday in an aeroplane but take rockets to space? And the sort of question exposes a bit of the issue that we call rockets. That's sort of a bit of a giveaway. Everyone goes to space in rockets, and the real question is why is that? So if we look at a typical trip on a plane to Tenerife, about a third of that weight is payload, passengers, and it's going to cost you around £5 per kilo to get there. But going into low Earth orbit, it's more like only 4% is payload, and it can be somewhere between 2,000 and 3,000 per kilogram. Now, admittedly, the destinations are somewhat different, but you know, the point is still moot that it's £5 per kilogram as opposed to £30,000 per kilogram. Part of the reason is all the jet has to do, the jet engine of the plane has to do, is to propel the aeroplane down the runway to such a speed as that the airflow over the wing generates enough lift to overcome the weight of the plane. This means the engines can be relatively small, so they use little fuel, so you don't have to carry as much fuel, so that the plane is then lighter, which means you can have smaller engines. And it's a virtuous circle, and that's why you get to this figure of around 30%. However, for a rocket engine, the rocket has to provide all the lift. There's no wings. This means you need big engines using lots of fuel, which means you're heavy, which means you need bigger engines and more fuel, and that's a vicious circle. The trouble is, jet engines don't work in space. So rockets it is. And when we think of a space rocket, we think of this shape. Rocket powered, bullet shaped, and fins at the back. And that's probably because of this thing, the V2 from World War II. But modern rockets aren't bullet shaped and don't have fins. So first of all, we'll have a quick look why that's no longer the case. So back in the 40s, the only thing to go as fast as a bullet was a bullet. So bullet shape was the starting point. And as shown here in the X1, the Bell X-1, the first craft to break the sound barrier in level flight. Though I point out it wasn't a world record holder because it couldn't take off on its own. And even more damaging for it, it was a rip-off of a British plane called the M52. It never flew, but most people believe it would have beaten the Bell X-1 to break the sound barrier. This British design would have been able to take off on its own. It solved the main problem of transitioning through the sound barrier in that the rear horizontal surfaces moved as a slab rather than little flaps at the back. Can you see the red pointer, by the way?
Yes.
Yep. But they were ordered to give all the designs to the US and shut their program down. And this is towards the end, probably just after the war. So potentially we could have beaten the Americans. It was going to be flown by an interesting character called Eric Brown. He's probably flew more aircraft types than any other person in history or any other person ever will. And also the first guy to land a jet on an aircraft carrier, a fluent German speaker, and he was in Germany, I think, at the time of the outbreak of war. And his book's well worth a read if you're interested in that sort of thing. So the downside of a bullet shape is that it's quite an expensive shape to build. It's got curves in two directions. It's an inefficient use of space. You've got all these funny corners. Well, not corners, that's the wrong word. All these funny shapes to fit things up against, these curves. And our knowledge of aeronautics has improved. And our ability to solve the aeronautics equations has improved. So no longer bullet shaped. Fins. What about fins? Well, fins work like a weather vane. So a weather vane points into the wind. A westerly comes from the west. If the weather vane is set broadside against the wind, the force on either side of this yellow pivot point is different due to the different sizes of area that the wind's going to hit. It's like different sized sails. The bigger sail is going to win, and the wind is going to force that bigger sail to be pushed away from the wind, forcing the smaller sail into the wind. This, what we call the center of pressure, is behind the pivot point. And to explain that a little bit more, so the center of mass of a free floating body is the pivot point for that body. Its center of pressure, because its shape is symmetric, is also in the middle. So those points coincide. But if we were to put some lightweight fins on one side, now instead of the sails being even on both sides of the pivot point, we've now got a lot more surface area on this side. So this side, the back of the now rocket shape, this is the bigger sail, if I'm not mixing my metaphors too much. And any wind coming into contact with this shape will push this side away from the wind. The center of mass moves slightly backwards because we've added a little bit of mass here, but the center of pressure moves significantly further backwards. And now we have a much bigger sail at the rear. It's like a weather vane, and because of the rocket's speed, it's creating its own wind. The rocket will correct any slight deviations. It will tend to be quite stable in flight. And in this picture, showing something similar, is a shuttlecock moving from the left to the right. And due to the wind of its own motion, is causing the big sail, the feathers, to spin behind the head. And that's why you always, if you manage to hit the shuttlecock, you're hitting it on the head. And just like the long stick of a firework rocket, this acts as a fin, forcing the rocket to point into the wind. So, you know, have this in mind when you're setting off rockets. You've got a pretty reasonable idea of where it's going to go towards the wind. So real space rockets don't have fins, which are a dumb stability measure. They add weight, but really have been superseded by vectored thrust. They aren't bullet shaped because that's an inefficient use of space and quite expensive to build. But not surprisingly, they do have rockets. So we'll have a quick look at rocket motors and jet engines. So how do they work? Well, both work on the same principle, just like letting go of an inflated balloon. The mass and speed of the expelled air coming out of the contracting balloon gives speed to the mass of the vehicle, the balloon, to go in the opposite direction. For the same mass and speed of exhaust, a lighter vehicle, a lighter balloon, would go faster. And the goal of rocketry is to make the vehicle as light as possible so it can go as fast as possible. It's the same as a cannon's recoil. A cannon fires a cannonball in one direction and the cannon recoils in the other. And if you could make a cannon do a succession of recoils, you've sort of invented an engine of some sort. And this is all to do with the conservation of momentum. The momentum is mass and velocity, and you need an equal and opposite mass and velocity in the other direction. So a light cannonball going very fast will move a heavy cannon, but just not as fast. And this form of engine, called a pulse jet, did exist, used on the Doodlebug, the V1, during the war. And the sequence of explosions gave it its distinctive sound. I'm pretty sure, though, that this picture's a false one. It's trying to show an interception technique of where the pilots would just tip the wings of the V1 and send it off course. And surprisingly, there was a manned version of this plane. I think, though, that was more for testing purpose. I don't think there was any mention of suicide type kamikaze missions in it. So briefly, I've used these terms. I need to give a bit more detail. So what's a rocket? A rocket consists of fuel and a source of oxygen, an oxidizer. The fuel and the oxygen combust, burn. Hopefully, if you remember your fire triangle from school, where you need a fuel, an oxygen, and an ignition source. So we've got fuel and oxygen. We can easily supply an ignition source, and then we're going to get combustion. And this means in the combustion chamber, we're going to have lots of pressure due to the hot gases, and that's going to force a mass of combustion products at high speed out of the nozzle. And the reaction to this is that the rocket moves forward, just like the recoil of a gun. Momentum is the combination of mass and speed. So high speed exhaust means a much bigger mass of the rocket moves in the opposite direction, but with a lower speed. The lighter you can make the rocket, the faster it will go. I think I seem to have labored that point a bit, sorry. An early rocket plane, which was very light, was the Messerschmitt 163 Comet. This used high test peroxide. That's the same stuff you bleach your hair with, if you're into that sort of thing. And methanol as its fuel. It was very fast, but had limited endurance. It would rapidly climb above the bomber force. It would dive, attacking the bombers, climb again unpowered, just using its momentum, dive again, attack the bombers again, and then glide into land. So it was fast, but had very limited endurance. The UK's only satellite launcher essentially used the same fuels as the Messerschmitt 163, which were kerosene and high test peroxide, and launched a satellite called Prospero. These are kerosene, called the hydrocarbon fuels. They're simple to work with, the liquids at room temperature, they're easy to store, easy to pump around to get them into the combustion chamber, but they're not as powerful as liquid hydrogen. The trouble with liquid hydrogen is it's very cold, needs lots of insulation, which adds weight, needs special pumps, and you couldn't really have a rocket, in this case a missile, sat fueled with liquid hydrogen ready to go for any length of time, as the liquid hydrogen would leak. And this choice of fuel was a legacy of the Black Arrow coming out of the Blue Streak missile program. You know, when the Russian missiles were landing, we couldn't say, hold on a minute, we need to fuel our rocket with liquid hydrogen. Can you not blow us up before we can release our rockets? So the British, went down the easier, simpler and cheaper route of kerosene and HTP, though not as effective because the range wasn't good enough. So this was a bit of a blind alley, and in the years that intervened, liquid hydrogen and liquid oxygen are now the mainstay of rockets, alongside some solid fuel boosters, as in the space shuttle. Another jet of comparable age to the Messerschmitt another plane of comparable age to the Messerschmitt we've seen is the jet-powered Meteor. Not as powerful or as quick as the Comet initially, but it had far better endurance. And this is a sort of recurring theme. Rocket engines are powerful with little endurance. Jet engines have more endurance, but not quite as powerful. Another dead end to compensate for the lack of power in a jet engine was this airplane Saunders Row Sr-35. It had a rocket engine for rapid takeoff and interception of Russian bombers, but a small jet engine to fly home. But again, that was soon superseded by the Lightning, which had no problem climbing to high altitudes. It had two huge jet engines and was very fast, so another dead end. But again, highlighting the issues that rockets are powerful, jets are not so. So we've looked at rockets which have fuel and oxygen on board, forced into a combustion chamber. The jet engine's slightly different because it takes its oxygen, its oxidizer, from the atmosphere. To do that, though, unfortunately, the jets at the front end of the jet is a little more complicated. There's lots of turbines compressing the intook air. So the front end's a bit more expensive. Back end really is just a tube, to be honest. The trouble with jet engines is as you start getting faster, the incoming air, which needs to be slowed down to roughly a stationary speed with respect to the engine, as a consequence of that slowing down, heats up. And at Mach 5, for example, that heating effect would turn the air to 1,000 degrees C. And then this machinery here would not be able to cope with air coming in at 1,000 degrees C. And even exotic new materials probably wouldn't be able to cope with that, with the tolerances required in all this machinery. So we can't make a jet engine to go that fast. So jets are limited to around Mach 3. So why we can't use jets to go into space? In effect, the machinery would melt. There are some forms of jets called ramjets and scramjets. They can get you going faster. They don't have the compression bit at the front. They just use the speed of the plane to scoop up enough air and compress it. But unfortunately, they don't work at low speeds. You have to be going supersonically for them to start working. So if you wanted to use scramjets, you'd have to have a normal jet engine to get you up to a speed. So that's a bit of a dead end too. So it's back to rockets. And so we really need to make them lighter. And one way we can do it, instead of having one big fuel tank and one big oxygen tank, we can split them into smaller tanks. And once we've used all the fuel of one pair of tanks, we can discard it. and then the remainder of the rocket is much lighter and can go off on its merry way, hopefully far more efficiently than if it was having to carry the discarded the discarded tanks. Sorry, just let me go back. I've missed a bit there. And the added bonus of this staging is that you can tune the nozzle to work more efficiently at the altitude it's been used at. So we talked about this combustion chamber producing a high pressure, forcing the gases to be exhausted. And this nozzle section, the reason that's there is that that has to expand the gas so the pressure is equal to the outside pressure. If the pressure in the expelled gases is higher than the pressure outside, the pressure will force the gas to leak out sideways. And then that gas is not pushing you forward because it's going sideways, and there'll be a reaction in the opposite direction, will be sideways in the other direction. What you want is all the gas coming out, straight out the back, all parallel. The ideal would be to have it, in this case, ideally expanded, so the pressure equals exactly the pressure outside. Over expanded, the problem with those is that it makes the jet unstable and you could lose combustion, which wouldn't be a great way of getting forward. So the safest bet is to actually underexpose. It's not as efficient as you would like, but it's the more stable and the less risky way forward. But still, even though you're slightly underexpanded, the nozzle you would want to use at liftoff would have a different shape to the nozzle you'd want to use when you're at or near orbit. And so this staging is helped by having different nozzles from the different tanks. And staged rockets are effectively the only way we can currently get into space. So there was a dream for the space shuttle. Though it was a staged rocket, it was designed as a reusable system and makes achieving orbit cheaper the more times it's reused and the more flights you make. And in Peter Ray's recently completed three-parter on the shuttle that we've enjoyed, we learned the original concept was for a wholly reusable system. Though the space shuttle was undoubtedly a success, but because it used rocket engines, they're so inefficient, and jet engines don't go fast enough, the budget just didn't allow for the full development of the concept to overcome these issues. So to summarize different engine performance, I've got a graph. I have got no equations in this talk. I'm sure some of you will be happy about, because I do like my equations, but this one's got no equations, but we do have a graph. And this specific impulse, read efficiency. So the higher the number, the more efficient it is. And obviously Mach number, the higher the number, the faster it goes. So the General Electric engine on a 747 is really efficient, but is below Mach 1, not supersonic. And those sorts of engines, turbofans, basic jet engines, don't really go much over Mach 1.5. To go faster than that, you need engines like on the Concorde or the SR-71, which have an afterburner, and they can make you go much faster, but they're not as efficient. Still, with the jet sort of design, we've got the ramjets and the scramjets I mentioned earlier. They can go faster still, but they can't get you from a zero speed start. They only work once they're going at speed. However, rockets, they can go at practically any speed you want, but they're always quite inefficient. And this is the problem with getting into space. The only thing that can get us there are rockets, but they're very inefficient, so they can only get a very small payload into space. I will mention something that we'll discuss a bit later. This line here is a theoretical maximum for hydrocarbon fuels, the kerosene, the normal aviation fuels, whereas liquid hydrogen, its curve is up here. So shows how much better hydrogen as a fuel is compared to the hydrocarbons. So I keep talking about needing to go fast. Why do we need to go so fast? So Newton's equations are quite simple, and escape velocity from the surface of the Earth is about 25,000 miles per hour. And what does that mean? Well, if I have a cricket ball and a cricket bat and I hit it, the ball goes up in the air, and what comes up must come down. If I hit it a bit harder, it'll go up a bit higher, but it'll still come down. To stop it coming back down, I have to hit it at the escape velocity. Well, actually, I'd have to hit it a bit harder because there's air resistance. So, I was never very good at hitting a cricket ball, to be honest, so I don't think I'm going to get 25,000 miles out of it. It's also the impact velocity. So something from outside of the Earth, just on the edge of the Earth's gravitational influence, if you just give it a little push and then it starts rolling down the hill into the Earth, would hit the Earth at 25,000 miles per hour. Actually, a little bit less due to drag. But it's got nothing to do with escape velocity. You don't have to go that fast. Escape velocity is the speed of an unpowered craft would have to achieve to escape. But rockets aren't unpowered, so they don't have to go that fast. Plus, you're only going into an orbit. You're not trying to escape. So that's a definite upper limit on the speed we need to achieve. Now, orbital speed is about 1.4 times smaller than escape velocity. So for any orbit, you've got a given speed. From that orbit to escape, you need to go 1.4 times faster. Root 2, it really is just root 2 in the equations. On the Earth, at the surface of the Earth, that means the orbital speed of the surface of the Earth is around 17,800 miles an hour. That, incidentally, is the max speed you'd attain if someone drilled a hole through the center of the Earth all the way down and you decided to jump down that hole. It's actually the vertical component of the orbital speed, and when you're at the center, the vertical component's vertically down, and it matches 17,800 miles per hour. And your period of oscillation to go from England to Australia and back again is actually the same as the orbital period. Bit of an aside, but so the orbital speed is only part of the problem. And hopefully Newton's cannon will help explain. So, got a nice cannons again, and you fire a cannonball and it falls out the cannon and hits the ground. Fire it a bit faster, it goes a bit further before it hits the ground. If you fire it with just enough speed, it will be falling towards the ground as quickly as the ground's moving away from it, and it will hit the back of the cannon. This model's fine, as good as it goes, but the trouble with it is that the cannonball is already in orbit. It's already at the top of the hill. You know, you have got to get to that orbital speed at the right altitude. And to try and explain how we do that, I need to do a little bit of mechanical energy. So, hopefully we all know where a pendulum is. Maybe a bit for Lewis to know what a pendulum clock looks like. It might not be familiar to him. But we've got a mass on a light inextensible string. if I give that pendulum some gravitational potential energy, I lift it up from its lowest point, I've done some work on it, and release it, at release it's got 0 speed. Its kinetic energy is 0, but it's got its maximum gravitational energy. As it falls, it's losing that gravitational energy and converting it into kinetic energy. It's speeding up. And when it gets to the bottom, it's converted the maximum amount of gravitational energy into kinetic energy. At max speed, maximum kinetic energy, lowest gravitational energy. But it's got speed at this point, and momentum takes it through this low point, and then this kinetic energy is converted back into gravitational potential energy until it gets to the high point and has 0 speed, maximum gravitational energy, and then falls down again, swings backwards and forwards ad infinitum, sort of ish. It'll eventually stop. So the pendulum has mechanical energy, and this mechanical energy is a combination of its position in the gravitational field, how high it is, and its speed. The total mechanical energy is constant, but continuously changing from all gravitational potential energy at the high point to kinetic energy and some gravitational potential energy at the low point. So the two components of an orbit are the kinetic energy due to its speed to maintain that orbit, the orbital velocity, and the gravitational potential energy you've had to give it due to its height above the Earth, the height of the orbit above the Earth, or whatever we're orbiting. And this explains Kepler's third law, really. If we have a circular orbit, the height above the orbited object, if that's a phrase, is constant. So there's no change of height, there's no gain in or loss of kinetic energy, so it goes at a constant speed. If we take a more eccentric orbit, take this point, apogee, it's the furthest away, it's got the most gravitational energy, but the lowest kinetic energy. It's moving quite slowly. It's moving quite slowly, but suddenly it's falling down, getting closer and speeding up, speeding up, speeding up as it gets closer and closer until it gets to perigee, its nearest point. It's got its lowest amount of gravitational potential energy for its highest kinetic energy, and the momentum then throws it back round and it's converting again its kinetic energy into gravitational potential energy into height above the object it's orbiting. So there's this interplay between speed and height that's explaining the change in speeds of an orbit. Okay, so not to labor the point too much, a jet is efficient, so cheaper, but cannot go fast enough and cannot go into space, but rockets are inefficient. So in the early 80s, the dream of the reusable space plane was revived in a concept called HOTAL, Horizontal Takeoff and Landing. It was a combination of Rolls-Royce and British Aerospace. It used what's called a dual mode engine. It was a mix of rocket and jet engine. This was cancelled in 1985. Ultimately, it failed due to the engines being right at the back. So all the mass is right at the back. So the center of mass was right at the back. And they spent a lot of time trying to compensate for that because all that mass at the back means the center of pressure is, if not in front of the center of mass, it was very close to being. And they had to do lots of work of trying to readdress that, and that just added more mass to the system, which in fact made the payload unsustainable and not worth doing. It made the plane want to fly like a shuttlecock and fly backwards. So that died, unfortunately, in 1985, and three key players, Alan Bond, John Scott, and Richard Varville, left Rolls-Royce and formed a company called Reaction Engines. And the dream carried on in something called Skylon. So Reaction Engines proposed a continuation of the Radical engine, both mixture of jet and rocket engine. And they moved the engines forward on, as you can see, the engines are now on the tips of the wings, and that solved Hotol's stability problems. The design was to be fully reusable, quick turnaround, single stage to orbit. You don't drop bits off as you're climbing, and it offered a prospect of cheaper space flight. Not only that, I'm sorry about the quality of this. This is taken from a rocket reaction engines presentation. Because you've got wings, you've got what they call the wide mission abort envelope. Something which, when you think about the space shuttle, it was lacking. You could return to base, you could abort downrange, you could abort very late in the ascent. However, current thoughts that the first employment of this new engine will be a twin stage to orbit, and that's what this is showing. So we take off from a runway, transition to rocket mode. At this point, the two stages separate. The Skylon returns to the landing site, to the launch site, and the upper portion, the upper stage, goes off into space. And to achieve that, we have quite a gentle climb in the thick, dense air. And then the rockets take over, and then we propel in the thinner air up into space. So what's this engine? It's called Sabre, standing for Synergetic Air Breathing Rocket Engine. It's got the fuel efficiency of a jet engine with the power and high speed ability of a rocket engine. Not quite. It can go from 0 to Mach 5 as a jet, and then from Mach 5 plus as a rocket. Now, just as a jet on its own, without the rocket portion, this getting from 0 to Mach 5 is a game changer. You know, there's nothing out there comparable. And you never know, one day, this is a reaction photo, but the name is mine and the spelling is mine as well. Quite jingoistic of me, I'm afraid. Just these engines in rocket mode may be able to power an airliner from London to Australia in, I think you talk about 4 hours or something like that, compared to the day it takes at the moment. And so why is this engine so brilliant? Well, to go back to the graph we had earlier, this being efficiency and speed, between 1 and 3 we're in jet engine mode. And the same jet can take us from takeoff all the way up to Mach 5.5. And I'll explain in a bit how it does that. The reason it's far more efficient than the normal engines in this range is because it's using hydrogen as a fuel. If you remember, I was saying hydrogen limits this curve up here somewhere. So this engine isn't necessarily far more efficient than normal jet engines. It's just better because it's using a better fuel, but it's definitely far more efficient than rockets, which are all the way down here. Then when we get to around Mach 5.5, this is when the air gets thin and very hot, and trying to get more oxygen out of the atmosphere doesn't really gain you much. We transition to a rocket engine, which unfortunately isn't as efficient, but is no worse than current rocket engines. So we've got all this profile here where we're doing things more efficiently, which means we can probably carry more payload. More efficient means less fuel and oxygen, because it's taking in its oxygen from the atmosphere here. We can have smaller oxygen tanks. Just, you know, if we can get this to work, great design. So what's the thoughts behind this dual mode engine? And all these slides coming up are from rocket reaction engines, sorry. So point 1, high-speed air entering the engine heats up as it decelerates to subsonic speeds. As mentioned before, at around Mach 5, it's about 1,000 degrees C. This air is pre-cooled, and the high temperature air comes from 1,000 degrees to sub-zero in the blink of an eye. And this piece of technology is the key, because it allows the jet engine behind it to be relatively straightforward. A bog standard jet engine with no real special alloys, just a normal jet engine, because the air coming into it has been conditioned. If the air wasn't conditioned, this engine would not be able to cope with the heat. So the core engine compresses the air mixes it with the fuel, and off it goes. Hot gases coming out the back. But we need to get rid of this heat that's generated, and we'll in a bit look at the clever way in which they reuse all this heat that they've taken out of the hot air coming in from the atmosphere. Not all of the air from the atmosphere is taken in. Some of it bypasses the core engine, and nozzles accelerate the airflow to high velocity, fueled by excess H2, and we've got some more impulse generated by this excess air. A separate rocket engine is employed. So when they go beyond Mach 5.5, near the edge of the atmosphere, there's no air. This cone moves forward, closing off the influx of air, and then its onboard oxygen is used, mixed with the hydrogen fuel, and it works then as a pure rocket. A common nozzle is employed for air breathing and rocket modes. Now, I've seen somewhere where this nozzle does change its dimensions. It's whether this lighter coloured section moves back or forward depending on which mode it's in. It's been difficult to find out. So whether they're being a bit cagey on that, I don't know. But the key to this really is this pre-cooler cooling the air, which means you can have a run-of-the-mill, just about, engine for the 0 to Mach 5. Don't need to be made out of any exotic materials due to this pre-cooler. So this is what the pre-cooler looks like. It's just like any other heat exchanger. You need lots of surface area, something cool running through it, and the hot gas flowing over the top of it. And the pipes in here are, the walls of them are less than the thickness of a hair. So they're really, really thin. There's lots of them, giving lots of surface area. And one of the major challenges they've had is actually joining these pipes together, bearing in mind this is running at hundreds of bar pressure. Because if you use normal techniques of joining, it'll just melt the walls because they're that thin. So some great work has been going on with this. Its job is to move 100 degrees air down to ambient, if not sub-zero. And they had a test demonstrator in America where they used the exhaust of a jet engine with afterburner to provide the hot equivalent hot air of flying at Mach 5, and this worked. And that's within the last year. This has all passed all its tests, October 2019, really happy. This key piece of technology works. But if I remember, we talked about this pre-cooler taking a lot of heat out of the air that's warmed up due to the compression. That heat needs to go somewhere and needs to be gotten rid of. And they do this in quite a clever way because they use that heat to do work. So this heat exchanger takes all the heat and puts in this green cycle is for helium. That's a closed loop of helium. Helium's not used in the process, it's just fixed in this loop. They take the heat of that, the incoming air, heat up the helium in the pre-cooler, and then they use that heat energy to do work by turning the oxygen pumps, the hydrogen pumps, and the compressors in the core engine. So this problem of the 1,000-degree heat has actually become a bit of an asset because they can use that heat energy. How do they cool down this air? By using cool helium. How's the helium cooled? Well, it's the liquid hydrogen fuel is used to cool the helium, and that's what this heat exchanger does. The problem with this, when you're taking off, you haven't got 1,000-degree air coming in here. So they need to use something they're calling a pre-burner, which is burning hydrogen and oxygen to create the heat in this cycle. And as the plane gets faster, the amount of pre-burner heat is reduced as the amount of pre-cooler heat increases to control the cycle. Also, these pre-burners have been tested and do work on the ground. They've taken a method of testing, of compartmentalizing the whole process and testing the bits incrementally. It's only now that they are beginning to design, not build, but beginning to design a test rig for the core engine. It's nothing like the size of the engine proposed for flight. This is just so they can swap parts in and out, maintain it easily, redesign if necessary. It's an open design to allow quick adjustments. Typically for a flight version, that's going to be much smaller, much more compressed, much more efficiently designed. But again, this is only at the design stage. Further development is in the rocket engine portion of it, and the main problem with that is that rocket engines haven't really been designed to be reusable. So how can we get the rocket chamber to be reusable? And as it says here, the turbo pump seals and bearings, they need to understand how to do that. Next step, they want to do they're investigating whether it's worthwhile doing what they call the hypersonic test bed, and that's just testing not the engine, but what they call the nacelle, is the outside of the engine and how that works on a small scale, unpiloted drone, for want of a better word. So there's lots happening, lots going forward, some great achievements so far in terms of the pre-cooler. But to be honest, after the pre-cooler and the pre-burners, there's still a hell of a long way to go. And reaction engines now are really only concentrating on the engine. So I don't think we'll expect to see a Skylon anytime soon, I'm afraid. But the dream isn't quite as fanciful as it was once thought. And you never know, the British might be at the forefront of aeronautics once again. Thank you.
Thank you, Ed. Reaction engines are a company very close to my heart. Alan Bond, unfortunately, has been, he officially is retired.
Yes. He's still involved with the company, but he's
Yeah.
not got a leadership role.
And I think one of the, as always, one of the worrying things is that the Americans now have a major stake in this, and under DARPA,
Yeah.
that's why the test. I'm going to say one of the test centres is over in the UK, in the US, isn't it?
Yeah. So that the test of the pre-cooler was done in America, unfortunately.
Yeah, but it's got to be said.
I think it's more they want to get hold of an engine that goes up to Mach 5. I don't think they're that interested in space with that, to be honest.
Yeah, but they have now an engine test centre in Oxfordshire, haven't they?
Yes. Yeah.
Yeah.
In the old rocket place. I can't think of the name. Rocket establishment.
I was going to say Cudston, but it's not.
Not Walton. I can't think. Sorry.
Oh, okay. So yeah, all good stuff. So, ladies and gentlemen, we're looking for questions. I've got a hand up from a gentleman called Andrew Devey. Andrew Devey, can you unmute yourself, please? Good evening, Andrew.
Good
Can
evening.
we have your question, please?
Yeah, just a first comment, excellent talk. Understood everything, which I'm surprised myself, but really I've enjoyed it. My question is, and Paul's mentioned it as well, now the Americans are heavily involved in this project, do you think it could suddenly go dark and be continued as a project for either the American and UK military?
Yeah, I think that's where, as I say, I think that the note to Mach 5 is a game changer. And if you think, I mean, I jokingly put a Concorde up there, but there's parallels. When you think of the Comet, not the 163 Comet, the de Havilland Comet from the 50s, late 40s and 50s, that scared the Americans and they wouldn't allow us to sell it to anyone. And then the 707 came along, a very similar capability plane, and they sold it to everyone. It's, you know, smacks of double standards, but I do feel that something similar may happen.
I think a word of caution before we all get very un-American and we have visits from Black Hawk helicopters and things like that, is that ESA has put in a lot of money into the project. And so the Europeans have got a vested interest as well. So there is a balance in there. But like you, my worry is that DARPA is involved. And the American law says that any technology that can be used as a weapon can be restricted.
Yeah. Well, after HOTOL, the engine design, the Rolls-Royce RB545 or something it was called, that was became under the Official Secrets Act. And it took Alan Bond a number of years, because the government wasn't doing anything with it, to get his patents, if that's the right phrase, back control of his patents.
Right.
So, and that can easily happen again. And ESA, yes, there's a plane, LAPCAT, I think it's called, which has been a test bed for some of these technologies. So ESA has been involved. British Aerospace is still involved. Rolls-Royce is still involved now with reaction engines. There's a bit of me that thinks it would have been nice if Britain could have done this. I know we're a small nation. We don't have the economies of scale, but it would have been nice. I know it's very jingoistic of me and nationalistic, but
I think at the moment there is the move that the government, or the British government, should sponsor projects like Sabre. And are they not setting up
the fund, yeah,
a new sort of funding for? I won't call them. I don't like the term outlandish ideas, but ones that are on the edge.
Yeah,
and
those that wouldn't normally qualify because they're not quite.
Yeah.
They're not going to get the returns in the same time frame that they would expect.
Yeah.
The more riskier ones, there's a pot of money available for them.
And I think it was our friend Kenneth Baker of the Suede Boots who closed down HOTOL, wasn't it?
Yes, it was.
So yeah, I think there's elements of optimism or reasons to be optimistic, but we have to be aware.
The base idea is brilliant. It's got somewhere to go, but progress is being made.
Yes. Andy,
Well, just a quick comment. I think they'll sponsor Sabre, so they've got something that they can rattle.
You know. Thank you, Andrew. Any other questions or any other comments? Tony Hudd.
Oh yes, a great talk. Very interesting. But what I'm confused about is this nozzle business and the pressure being equal between the gases coming out of the engine and to equal the air pressure.
Yeah.
Could you run me through that so I
Yep.
possibly understand it?
Yeah. If the pressure in the atmosphere is exactly the same as the pressure within the nozzle, the jet will not expand. And you don't want the jet to expand because it means it's moving in directions other than opposite to what you want to go. Now, what the thing is, you've got pressure is made up of two things. There's the static pressure and dynamic pressure, and understanding that may help understand. You might be thinking, well, if the pressure is exactly the same,
Nothing will happen.
it's not going to come out. It's
No.
holding it in. It's not quite the same. The different sort of pressures that you're talking about. The total pressure is static pressure plus dynamic pressure, and you have to. It's the difference between the two.
But if there was no difference in direction, then it would still work. So it might be a matter of designing another nozzle.
I'm not quite clear what you said then. Sorry.
Well, you're saying that it'll go in, it won't go in the opposite direction.
It will still go back in. The gas is going out to the left, and the vehicle is going to the right.
Yeah.
And that will always happen. If you under expand the nozzle, the gas, sorry, so you have the wrong design nozzle, a portion of that gas coming out will not be coming out in straight lines, for want of a better word. It'll be coming out at an angle. And
Yeah.
so all of that energy is pushing the vehicle in the right direction. Some of it will be pushing it slightly down.
But
Because it's out at an angle. You want it to come out all parallel to the direction of travel.
couldn't you just design some reflectors and deflectors?
No, the whole point
Make-
is it's leaking out sideways because of the pressure difference. That's why you need to make the pressures the same. So if it's got a higher pressure in the jet compared to the atmosphere, then the jet's going to push against the atmosphere and splay outwards.
I want to know a little bit more. Another question. I don't know if it was the Skylon or before that you said when you had a jet and a rocket engine going up and the jet engine was jettisoned, leaving the rocket engine to carry on. But how does the rocket engine craft get back?
Just like any other rocket, I suppose. I think that was the twin stage to orbit version, where it's in effect got a Skylon with a rocket sat on top somehow. The Skylon takes off a bit like the 747 carrying a shuttle. When it gets to a certain speed and altitude, they separate, which is quite a dangerous maneuver, I think. The Skylon would come fly back and land, but the rocket would go into space. That's not necessarily has to be reusable. That could be just like a rocket, but that rocket has to do a lot less work. It doesn't have to get itself from 0 to Mach 5 and from 0 altitude to 20 kilometers, let's say. The plane does that more efficiently because it's got wings. There
are examples of that launch system used at the moment. Virgin Space uses I think it might be an Airbus, and it has an Airbus 380, and it has a rocket slung to the bottom, and it can get a payload into Earth orbit. The American military use it for their killer satellites as well. So it is it's a launch system that's currently used. So yeah. Okay, Tony.
Yes, thank you. What about other Tony?
Uh,
Is he contactable?
I don't know. We've got a question from Catherine. Unless
Oh,
we'll just take this question from Catherine, and then we'll get back to Tony M.
Right. When do you think the engine will be working?
I've no idea. I mean, to say they've only got, although the pre-cooler is an amazing thing, and this can be used in other industries as well, and that may be a way for them to fund more research. Yeah, you've got to be saying 10, 20 years, I would have thought, I'm afraid. But your guess is as good as mine. To be honest, you've all got about as much knowledge as I've got now on this, frankly.
I think it might be a bit closer than you're expecting.
I would hope so.
So, yeah. So, all right, Catherine. Tony Morris.
Hi, Paul.
Hi, Tony. I thought you had a comment.
Well, I have, yeah. I saw Ed's comment, people trying to get hold of me. Unfortunately, the beginning of Ed's talk clashed with the end of a Institute of Physics talk on the LIGO black hole detection. Anyway.
You were watching EastEnders, just own up.
Okay, couple of points. When the UK they're looking to put £800 million into this like blue skies thinking for entrepreneurs that may not come up with projects that make money. Well, for those of us of a certain age, we can remember back at the NRDC, National Research and Development Council. Now, so unfortunately, we've got a really spotted history with this, of having certain things set up and then a government or a treasury of a different flavour then cans the project.
That sounds about right.
Yeah, so the Science and Technology Facilities Council, that's no longer that, and that's disappeared within the last few years. I mean, we used to see the outreach, certainly for in the amateur astronomy world, you know, the leaflets and stuff we used to get from, all that's been canned. So I'm afraid the American model where the venture capitalists or the vulture capitalists come in and do the speculation on it is why these things tend to move to America, I'm afraid.
I mean, at the end of the Second World War, we were leaders in aeronautics. And from then on, there's been a series of great leap forwards that we never grasped.
Yeah, but we weren't allowed to. So, you know, on the Manhattan Project, soon as, you know, the atomic bombs have been unleashed, what did the Americans do? They then made it an American-only project. Yeah. So ourselves and Canada, who were heavily involved, had to scramble to develop our own technology, which luckily we already knew because we provided some of the key scientists for the Manhattan Project. Yeah. You know, those of us fortunate have been to Woolmerah, we can see the debris of the British space attempt there. You know, and as you mentioned, you know, a lot of our research and development was stopped and taken to the US.
Yeah. You know, we were doing things on re-entry of missiles far in advance of what the Americans were doing. And they just took all our information and said, oh, you can have a Polaris now. You got to pay for it. You know, we give them all the information and we had to pay for stuff. It's littered with it where, you know, getting Prospero into space, our only satellite launch, was done on a real shoestring, you know, and you'd have people in the ministry complaining, oh, they want another £20 for this, literally to that. TSR-2, a man in the ministry wanting to design the cockpit of the plane, saying, oh, I want the altimeter there. And yet professional airmen saying, look, the cockpit, it was like saying, let's put the accelerator on the left, the brake in the middle and the clutch on the right. and they expect everyone to be able to drive. You know, it was the incompetence, I'm afraid, of the government thinking they could run things which they couldn't.
Yeah, but unfortunately, we can see it now with ARM, you know, the ARM Corporation.
Advanced Machines.
Yeah, yeah. So that is going to become an American company.
Yeah.
I thought it had been sold to China.
No, it was sold to the SoftBank in Japan.
Yeah, but I thought the SoftBank was trying to sell it to China.
No, it's Nvidia, I think, are trying to buy it.
Right.
So they've already got their own engineers that use, you know, the ARM development set. So we know what's happened to that.
Yeah.
I can feel it in my water.
Time and time again, we've led the way and just given up, or given it to someone else to make all the profit on.
It's a strange phenomenon, that. I just don't know why we can't seem to make that last push.
Yeah.
Well, maybe now that we've stopped paying the Americans back for our war loans, we might develop a bit of a backbone and start doing it ourselves.
That is a big issue. The fact that we were so indebted by the Second World War and only really just recovering from it.
Yeah. Well, I think we only paid our last lump of money back to them about, it might have been only about 6-7 years ago.
Yeah.
So maybe we'll grow a bit of a backbone now and get on with things on our own. Going back to Prospero, very interesting, that little satellite. Apparently it was launched into a nearly perfectly circular orbit, and they turn it on every now and again. So if you keep an eye open on the radio ham websites and things like that, they will announce when the transponder's working. And if you can pick up, I think it's 137.56 megahertz, you can hear it go beep, beep, beep at you as it goes overhead. Apparently its orbit is so perfect that they're expecting it to stay in orbit until 2070. There's no orbital drag.
When did it was about 71,
71, I think it was.
Yeah.
It was launched. So yeah, it's still out there. It's still out there going beep, beep. There was a plan to try and reactivate it, but I don't think the Ministry of Defence was very happy about the idea. Ladies and gentlemen, have we got any other questions or comments on tonight's excellent talk? Tony Hood.
Yeah, just to mention to Ed that I have had some involvement with jets at school. Well, no, at school, while I was at school, we used to make planes such as Gloucester Javelin and stuff like that, and using JetX engines. We used 2 different sizes for different models, and they were solid fuel, really, with the fuse that you used to wind onto the pellet and then put them back on and light it. And I used to fly them by themselves without the plane as well. And they were great. So I just had a bit of involvement there.
Wow.
Why bother with a plane? Let's just get the engine in. Right. Thank you for that, Tony. That's a lovely picture. And Phil Buffett, can we try you again?
I don't know. Can you hear me now?
I can hear you, Phil.
Oh,
Go ahead with your question, please.
Yeah, it was just something funny I heard. I watched a programme on Concorde the other year, and what I found tickled me was the captain, #1 captain flying Concorde, says, "It makes me laugh when we're flying over America. I'm flying at 60,000 feet in a shirt, drinking cocktails and drink champagne." And he says there's 2 U-pilots in spacesuits drinking through a straw. And I think that sums Americans up quite well.
Well,
if Americans develop it, you're going to have to wear a spacesuit when you fly.
Well, there you go. So, can we give Ed Bothamley a huge thank you, and thanks for winding the year up for us, Ed.
No problem.
Thank you, Ed.
Thank you.